Hey guys, this is JSer. How's everything going? In this video, I'm going to take a look at the top Facebook questions. This is the second video of a series of a quick recap on top Facebook questions. I've already done the top 10, so in this video, it's about from question 11 to 20. So let's start. 269, Alien Dictionary. We're given a list of alien words in a lexical order of a foreign language, alien language. So we need to deduct the order, right? The alphabet order. So this in this wait a minute. So the idea is not complicated. We compare each pair of the word and get actually at one the order information between two letters. Like for this one, it will be TF, so T must be smaller than F. So we will create actually, if we think of the character as a dot, a node, then actually this will be like a direction graph, right? This is the edge from T to F. So we loop through all the words and get the map, get the graph, which we can store them in a forward map. And okay, so this one is better, I think. Yeah, we use a forward map, and to be useful, we use a backward map to make it two-way. And then we loop through all the words and get the direction, collect the alphabets, and yeah, compare with the previous word to get the paths. If we find the first different one, we update the forward map, update the backward map. If we met something, this is the invalid case, which j equals to length and j is not equal to length. So what does this mean? Wait a minute. What is j? J is from I is word's length. J is the word's length. We compare to pair one. J is the word's length. So j is the j. If j is met and j is not equals to previous ones, then so previous one is longer than this one with the same one with same, so this one should be before, right? So this is invalid. Okay, now when we got all the forward map, and now we will start collecting the final result, right? We use the result and we check if alphabets. The idea is simple. If we first loop through all the nodes and find that there's no one pointing to it, the nodes which are no like a forward, like no forward to it, then that will be the start, right? The graph will be like a bunch of arrows. We just collect the arrow, yeah, the beginning of the arrows. So if we doesn't have the oh yeah, we use backward to check that. I'm sorry. We check it. If it doesn't have it, then this is the head, collected. Well, after collected, we delete it from the alphabets, right? And then after we delete it, we will need to update the forward map for all those nodes, right? So that's actually pretty straightforward. We first create a graph and start traversing through the graph. Okay, and this is a common technique in several questions, like a similarity of the words, something like that, destination, something. Okay, this is the next one is word break. So we're getting a string and a word dictionary, and we need to determine if they could segment it into space separated sequence. So either this word could be summed up to concatenate it to generate this string. Well, it's actually pretty straightforward. Like we just loop through all the string, and for each position we check if word is in it, right? And we keep a map, keep a map to see if that could be matched at a specific index. So it's like we look through the first one, we search for the words. If some word is met, then we update it. Okay, we index. Okay, well first we find the word, and we need to first check the previous one, right? If we start searching the words from T, then the index here means comma at here should be true. So if it's true, if this previous one is true and we found the word, we said is bracket is match is true, and then we can update the index, right? So, and after all this is done, we can finally return the comma tag. This is a variation of this solution. Rather than for each index we search all the dictionary to try to match that. Actually, we could do what? We could just check all the possible substring in the string and check if it is word has it or not, so that we can transform the dictionary into a set. And yeah, you see, we loop through all the index, and we just loop through the index backwards, right? To make each as a start index and to get the substring and check if it exists or not. So this one is based on looping through all the words. This one is based on through all the substrings. So basically they should be the same, but if the word, if the dictionary is very long, we checking all of them for each index is not that performant. So if the word dictionary is longer, we check a word the dictionary is shorter, we check it against the dictionary. If not, we check by the substring. Okay, that's all for this one. We'll break, and this one is minimum window substring. While given as st, find the minimum window s, which will contain all the characters. Well, this is a sliding window. We actually need to first we traverse through the t, yeah, t to see how many characters are needed. Like a, how many a's are needed, how many b's are needed, how many c's are needed. So we use a target to count the occurrence of t, and then create a count of the sliding window we're going to do. And the missing characters is to the helper to see to determine if the string matches our needs. The target is you have to generate it. We don't touch it, so we use missing characters to see if it is done, right? And the indices is actually the okay. Wait a minute. So we loop through the target, and the set gets the target count. The missing characters, we add all the characters in the missing characters. Okay, now we loop through the string. We get the character. If the target has it, we will update our this count, right? That's for the sliding window. We update the count, and if the count is met, like 1a needs 2, and we found 2, so we will remove a from the missing characters, right? And we need to push the indices into it because we need to return a string. We need to know where they're to begin, right? So the indices will push the character and the index. If we have it, if the target has it, like a, we have a, then we push each character a and 0. Okay, so after we push it, if the missing character is 0, it means we have a match. So we get a possible result, which is a slide index 0, 1, which is the index, to all, right? So we can keep the indices of A, B, and C. So A, B, B, C. So we get the last index and slice it. So this is possible result. Update it by its length. And we will remove the first index, which is the A, possible, which is A. So we need to search for the next. We remove A and shifted it and update the count, right? If the count is not match our needs, we will add the missing A back to the set. So this will do over and over again. And when it is done, when this traversal is done, we have the minimum window. So cool. It's actually a bunch of map and set to keep track of the conditions. A key point is that we need to push the indices of each node, like A, B, and C, because that's the position we need to care. Suppose we have A, and we find ABC here. Now we need to remove A D 0, right? We could remove all of them until B. So that's why we keep track of all the indices. Okay, minimum window is done. We will go to 3, 4, 5, 6, 7, 8, 9, 10. Okay, this one. Verify an alien dictionary. We alien language surprisingly use it. So this is the alphabet, then the order. We need to compare if this one is lexicographically before LeetCode. Well, I think it's pretty simple. We first transform the order, the alphabet into a map, right? And get the order map to. So H is 0, L is 1. So we can get the comparison, and then we can hash them. Okay, we can hash them with 26 base numbers, and we transform all the string into like 21, 0, 1 something, and we hash them, and then for each one we just compare them, right? So this is OM, and also we could actually we can actually real order is list, we get it, and translate, okay, for each seg. Real order. Actually, we can translate them back. So for each edge, for this one is 0, so we can translate them to A, right? And then we can use built-in the lexical compare. Or we can check this. The basic naive solution is, of course, we use a map to keep track of the index, and we can create a helper method called compare word to determine if they are true or not. So we can loop through all the digits and compare each index if they match our requirement. If compare character is this, if we found it, we return 1. If not, we return -1. And there's a special case that the other one they can like one is containing another one. So the longer one should be larger, which should be put at the end. Should be put later than the other one. So we loop through all the words, compare. Okay, that's done. And then we need to add strings. We need to add two numbers, which will be represented as a string. So we need to do the naive adding operation. So, okay, for each number, the maximum would be considering one carryover, one carry. We initialize the result with extra 1 digit, and then we loop through backward, and we parse each digit to 10 base numbers, and then we sum them up. Don't forget the carry. This carry is global, and we sum them up. If it is bigger than 9, we update the carry and update the sum, set the sum, and finally we check. Don't forget to check the leading 0 problem. If not, we shift it and then we join. Yeah, that's all. Kth largest elements in an array. Well, this is a quick select. The idea is that we could do binary. We do quick sort, and we choose a pivot and move the smaller numbers to the left. Because we're case large, so the largest numbers to the left and smaller numbers to the right, right? But if we found that the index is equal to k, we can return that one. So that will be faster than any other solution, I think. So the idea is simple. We do something like a quick search. So first, a quick select, a start index, end index. We choose a pivot, which is actually the start. Now we keep track of the insertion index, which is from the next one, and then we loop through all the numbers. We start one with all the numbers and check if it is bigger than the pivot. If it's bigger, then we swap it, right? We swap the index with the insert index. This is not the pivot, but the index. This number is the pivot, but we swap it with the index and move the insertion point to the next one. And then after all the insertion is done, we we will update, we will swap the start with the insertion index, right? So that all the bigger numbers to the left, smaller numbers to the right. Now we will see, we check if the index is a satisfy our k. If it's bigger than k, then the k falls to the left part. So we do it recursively like this. Start, remember this is insertion index -1. This -1 is the insertion index. So we insertion 2. This is the boundary. Or we check the other half, and this is the check, right? If we found that the insertion index is the same as k, we return it. So, and this is util function. So yeah, it's quick select. Binary tree right side view. We have a binary tree. We need to get the result. Get the array of the numbers. If we look at the tree from right, so this one from right, 1, 3, 4. But this is a plain BFS solution. We put them in a queue, and for each round of traversal, we set a variable called rightmost file and update this file. And if they have children, we put them into the queue and do it for the next round. At last, we will collect the result. So this is the result. We use a null to identifier. Use it as an ending identifier for each layer, or we can use the index. We can count it. We can do this by counting or check null. This we should do here, right? 3, 6, 9, 10. Here, merge sorted array. For this, nums 1, nums 2, we need to merge nums 2 to nums 1, and nums 1 have enough space. Because you have enough space, we need to keep the index untouched. But if we start from left to right, this index will be changed, right? So we actually do it backward to compare the numbers at the rear, and put the biggest one to the index. Index is actually determined by the none, right? So m-1 and -1. So the index will be m-1 plus n-1 plus 1. So just to pick the bigger one, set it, and it will be done. Binary tree maximum path sum. Wow, this is a recursion. So for the max sum, we consider the roots and the possible path. There's two possibilities. The element is in the path, or the element is not in the path. If the element is not in the path, then it should be in the left or in the right, right? So we use a recursion set compared to the max left or max right. Right? So, and if it is used, if it's in the path, then it might be this element alone, or this element plus left tree, or this element plus right tree, or this left tree, root, right tree are all counted. So actually the possibilities are 6. One is itself, or itself with left, or it's left with right, or left only, or right only, or left, right are all used. So for these recursion function, we will return two things, where one is the max of what we want to get, and the other one is max if the node is used, right? So this tree will return the max in the whole tree, but max connected is if it is used. So we need to, so you see, if we are going to get the max connected, we only see if it is only it is used, or this used to the left together with the left, or this one with the right, and then we return the max. This max actually could be put globally. This is the original solution, return max and max connected, but actually max could be set globally, and we only can return the max connected, which means the node is used. So this is it. Recursion. Remove invalid parenthesis. We're given the typical parenthesis problem, but we need to output the valid parenthesis if we are able to remove some pairs. Remove some parenthesis. Well, because we need to return all the output, if we don't need to, we just return boolean or the count, we could just do the counting and do nothing. But now we need to return all the strings, so we need to keep track of the index, which parenthesis is actually removed, right? Sure. So we create. Well, first we get all because we might have some alphabet. We first loop through all the string to check where the parentheses are with indices of parentheses, and then we use a set to keep track of which parentheses are removed, right? So actually the solution would be we loop through all the parentheses and try to remove it. If we remove it, it might generate a possible result or not. If not, we continue remove it remove one of the parentheses to the right? So the final for loop is loop through all the parentheses and try to remove some of them. If you to remove a parenthesis, what we do? Okay, so we keep track of the mean moves to avoid terminate it as fast as we can. If it is we update the mean moves, and if it took more than we need, because we need to return the minimum, right? So we stop. And after we move one, we add the index to the wait a minute, to filter indices, and we call it is valid to check if the string is valid or not. Here we just do what we do. We just count the left parenthesis and right parenthesis, right? If we find it's valid, then we can just return the string, right? You see, for each letter, for each character, if it is filtered out, we continue. If not, we push the valid string, and we count the left and right. If it doesn't match, we return false. With the empty string, if true, we return the final string. So we check if it's valid or not. If it is valid, and the indices count is smaller than mean moves, we update it. We remove it because they are not valid, right? So we remove it. And for the other cases, if it's equal to mean moves, we add it to the result and update the mean moves, right? Yeah, if it is smaller than it, we clear. If it is smaller than, actually it is smaller than it, we clear. And if it could be used to update it, we update the mean moves and add the result. And if it is not valid, it means they still has we have still possible to remove one of the next parentheses. So we continue doing the try removal, here. And don't remember, because we're using backtracking, we need to delete the index from the filter indices set. So keep the options, not let's say keep the strings untouched to revert it. And and last, there's a special case of if we do nothing, is it valid? So we check it first, right? And finally we return the result. Okay, so that's the 301. So from these 10 questions, there are actually several hard problems, but they are pretty straightforward if we remember how we should do it. Okay, that's the second video of my series. Hope it helps. See you next time. Bye-bye.